Now let's apply our steps for equilibrium analysis to a three-dimensional problem. The steps do not change from a two-dimensional analysis. The first step in our equilibrium analysis is to state the goal of the analysis and determine the system of interest. Here we're given a rigid pole with cables connected at G, A, and C. We are asked to find the tensions in the cables contacting the pole. In order to solve for these, we will isolate the pole, therefore the tensions will be reaction forces on our pole. Therefore, the system we would like to isolate is just the pole, excluding the cables. The goal of this analysis is to find the magnitude of the tension forces in the cable TG and TAE. Now that we've isolated the system of interest, let's draw a free body diagram. The first step I did was include an axis. I have all the relevant geometry by labeling each point position in XYZ plane from origin O. I've assumed rigid body and static equilibrium. The tensile forces are acting along the cable's line of action, and that for this analysis, the weight of the frame is negligible. Now I need to put in my reaction forces at O. We're given assume the absence of any resisting moments on the base of the pole O about the X and Y axes. So the problem statement is saying that there is no moment about the X and Y axes, but it can resist in the Z axis. Therefore, I'll put MO in the Z axis. It's also constrained in the X, Y, and Z translation, so I'll put reactions at O. Now that we've captured all the forces on the system, we may write out all the forces and moments as vectors. The tension can be written as the magnitude of the tension times a unit vector directed along that tension cable's line of action. So TCD is equal to the magnitude of TCD times the unit vector from C to D. I've written all the tensions out similarly. The reaction force can just be written as a sum of its components. So it's equal to ROX, X hat, ROY, Y hat, ROZ, Z hat. To find a unit vector along our force, we can use a position vector from the cable's starting point to their endpoints, since those positions are known. Here we'll go through it for you, CD. That is equal to the position vector from C to D divided by that position's magnitude. We can calculate that as the position D minus the positions at C all over the square root of their sum of the squares, giving us a unit vector along the line of action from C to D. Next, I will find the position vector or unit vector from A to E. That's simply the position E minus A divided by its magnitude, and the position vector from G to F. The last thing to do is write out my moment as a vector. Since there's only a Z direction, the moment about O is simply the magnitude of the moment of O times Z hat. Now that we have all our forces and moments that appear on our free body diagram written out as vectors, we can see that we have the following amount of unknowns. The tension in cable CD is known because we know the magnitude. The tension in cable G to F represents one unknown, since we don't know the magnitude, but we do know the direction. Similarly, in TAE, we also do not know the magnitude. We do not know the reactions at OX, OY, and OZ. So the reaction constraints for the RO forces represent three unknowns, and the magnitude of the moment along the Z-axis is also unknown. We have 6 unknowns. Since this is a three-dimensional problem, we have 6 equations that we can use to solve for these unknowns. Therefore, this is a statically determinate problem. I'll also write out the tension in cable CD by multiplying the magnitude times the unit vector that I've already found. Now that we have all the forces and moments written out as vectors from our free body diagram, we can begin to generate and solve equilibrium equations. How should we begin? we have several equations at our disposal. We have the resultant force on the system is equal to 0. That gives us three equations. The sum of the forces in the x would sum up to 0, the sum of the forces in the y equals 0, and the sum of the forces in the z equals 0. We also have that the resultant moment on the system at any point is equal to 0, giving us three equations where the moment about each axis would be equal to 0. If we're clever, we can avoid doing some work here and not have to solve for the reactions at O, since we were not asked to solve for them. How can we eliminate the reactions at O and at the same time solve for the tension cables at A and E, since they have force components along the same axes as the reactions at O? This leads us to think that we should not use the sum of the forces to solve for the tension along the cables. Instead, if we were to take a moment about O, the resultant moment about O, we would eliminate the moment from the reactions at O, since there is no lever arm to O. Stated elsewise, the reactions at O do not create a moment about the point they are applied. So the moment the system at O is equal to the moment from the tension in cable GF about O, plus the moments from the tensions in cables AE about O, plus the moments from the tension cables CD about O, plus the moment about O from our boundary condition. To solve for these moments, we can use the cross product. We can say that the moment from cable tension TG about O is equal to the position vector from O to G crossed with the tension from GF plus the position vector from O to A crossed with the tension in cable AE would give us the moment about AO from tension AE, and the moment from tension CD can be found crossing the position vector from O to C crossed with TCD. Luckily, these position vectors are very easy to find because the positions of G, A, and C are all given by the coordinates. These cross products can be done by taking a determinant of the cross product. This is easier for 3 dimensions than trying to do it on your own. I have set up the 3 cross products or determinants we will calculate for this equation. Carrying out these 3 cross products, I get the following resultant moment from the forces in the system about O. 0.832 Tg minus 2.89 kilonewtons x hat plus 1.664 Tg minus 1.342 TAE y hat plus 0.55 Tg minus 0.962 kilonewtons meters plus the moment at O in the z hat direction. This vector about the resultant moments at O can give us 3 equations. I can dot this vector with x hat, or think of it as taking the sum of the moments in the x direction. That would result in an equation that 0.832 Tg minus 2.89 kilonewton meters is equal to 0. Similarly, I can dot it with y hat, giving me a linear equation, and z hat, giving me a linear equation. The key here is that this moment results in 3 linear equations with the 3 unknowns I would like to solve for: TGF, TAE, and the moment, which I was not asked to solve for, but I can solve for now. With this set of 3 linear equations, I can easily solve for TGF, since it is already, there are no other unknowns when I take the sum of the moments in the x hat. However, I would like to show you a nice way to simultaneously solve multiple linear equations all at once, therefore avoiding doing a lot of work. Computers are good at solving systems of linear equations, so I would rather you spend your time doing something else than solving a bunch of linear equations. Here's how to do it easily. If you organize your set of linear equations where the first unknown is in a column, the second unknown is in a column, and the third unknown is a column, and set that equal to your knowns. That can be rearranged into a matrix form where you put all of the answers or all the coefficients of the first unknown in the first column, all of the coefficients of the second unknown in the second column, and all of the coefficients of the third unknown in the third column. Then you put the unknown symbols in the column vector next to it, and that is equal to this third column vector with your knowns. In linear algebra, we have a system AX, some matrix 3 by 3, AX multiplied by a 3 by 1 is equal to a B matrix 3 by 1. We can solve this by multiplying both sides by the inverse of A. That gives us X is equal to A inverse B. Solving a 3 by 3 inverse can be tricky, so I don't expect you to do it on your own. Luckily, there are tools for us like Wolfram Alpha that can easily do it. Here I've input my first row, my second row, my third row, and the B vector, and I'm taking the inverse of A. With one click, I can have Wolfram Alpha solve my problem for me. The result in the first place is my first column. This is the answer to my second column, and this is the answer to the unknown in my third column. So I have that TGF is equal to 3.47 kilonewtons, TAE is 4.3 kilonewtons, and MO is minus 0.962 kilonewton meters. I will post a link to the Wolfram Alpha solver. You can use it to solve more than a set of 3 by 3 linear equations. This can be easily expanded to a 4 by 4 by adding a fourth column to each row and a fourth entry to your B matrix. The final step is to ask yourself, does our solution make sense? We could take a moment about another point like we did in our other equilibrium analysis. However, that would require resolving for ROX, ROY, and ROZ, which we were not asked to do. We can also look at our solution from another point. The tensions we solved for were all positive, which means the unit vectors that we said our forces were acting along were correct. This is good. If we had received negative values for our tensions, that would mean that the forces we drew were actually pointing in the opposite direction. Since these were cables, that would not make sense. Therefore, it is a good sign that our tensions ended up positive. They also had the right units of kilonewtons, and our moment was kilonewton meters. You can see that by carefully following your units through. If your units ended up kilonewton meters for tension, then you should probably check your math to make sure you didn't come up with an error. Using these 5 steps, we can solve any equilibrium analysis. It is simply a matter of breaking it down into one step at a time.